Hello, calculus fans. Let's find the volume of the solid that's bounded by the plane z equals 0, that's just the xy plane, and the paraboloid z equals 5 minus x squared minus y squared. Notice that paraboloid is upside down because of the minuses on the x's and y's, and then the 5 tells us that we move the whole thing up 5 units. So let's take z equals 0 and put it into the equation of the paraboloid. We get x squared plus y squared equals 5. That tells us that the plane intersects the paraboloid in the circle x squared plus y squared equals 5. So the solid lies under the paraboloid and above the circular disk that's defined by x squared plus y squared is less than or equal to 5. Notice how we're making a distinction here between the circle and the disk. If we want to describe this in polar coordinates, we can. It's given by r goes between 0 and root 5. Theta goes from 0 to 2 pi. Let's take a look at a picture. This is not a picture of the solid, it's a picture of the region of integration. Next, we'll write down a double integral, and in doing so, we note that 5 minus x squared minus y squared is equal to 5 minus r squared in polar coordinates. So our volume is the double integral over d of 5 minus x squared minus y squared, and we convert everything to polar coordinates. That gives us the integral from 0 to 2 pi of the integral from 0 to root 5 of 5 minus r squared, r dr d theta. Don't forget the r. This guy right here, don't forget that guy. Everything factors nicely. We can separate out the thetas and the r's. And if you work out the integral, we get 25 pi over 2. Pretty straightforward anti-differentiation that has to be done there. If we had tried to use rectangular coordinates instead of polar coordinates, then this is what the integral would look like. And it'd be pretty messy to try to deal with this. In fact, you would end up having to compute something like integral of 5 minus x squared to the 3/2 power. And while that's doable, it's really messy. Okay, that's all for now.